Okay, good morning, everyone. We will get started with the review. Can everyone hear me? I can't see the chat. If someone could please come off of mute and let me know if you can hear me.
Yeah, we can.
Okay, thank you for confirming. So this is the Math 1326 review for the second exam. So the first part of the review will just be like overview of the concepts and kind of like a few steps walking through how you would solve them. And the second part of the review has example problems so that the steps that we just walked over, you will be able to use those to solve problems in the second part of the review. And in between, we'll have about like maybe 5 minutes of break. So let's get started. This is the topics that are going to be on your next exam. I was told by a few students that the professors have confirmed that the double integral problem, where you have to switch the dx and the dy, is going to be a bonus problem. So these are the topics that we will be going over today. So let's get started. I'll actually wait for like a few seconds just in case you want to take a picture of it or something or write it down. Okay, we can get started. So first up, we have improper integration. So the first thing to remember is that you will use your integration techniques just like you did on your last exam. Like you will use all those basic integration techniques. But the only thing to remember here is that you'll be using limits to solve these improper integrals because they range from an one bound to infinity or from negative infinity to another bound. So, and if it's from negative infinity to positive infinity, then you want to break it up at point C or just any point so that you can like split it up into two limits and solve those. So this just kind of like talks over all of that and what improper integrals are. So let's look at how you would solve it. So the first thing is that you want to set up the problem in form of a definite integral and limit, right? So for example, if your problem is from, let's go back here. Let's say your problem is from a to infinity, right? You want to set it up as a definite integral, as you see here in the right, where it's a definite integral from a to L. I know that in your classes you have been taught to use b when it's positive infinity. So you would do from a to b, and then your function, then you would do limit as b approaches infinity. So here your a would be a number. It would be like 3, 4, like anything. It would just be a number. And then it would be going to infinity, which you would replace with b or L or any other variable of your choice. And then the first thing that you will do is that you will just solve this integral, this definite integral as it is, and then plug in your values until you get to an equation. And then you would use the limit as b approaches infinity to solve the equation that you've got. So you like find the limit, and then you will, based on whether you get a number or not, you will say whether it's convergent or divergent. Always remember that limit as a number approaches infinity, and if it's 1 over a number, 1 over like x to the r power, and r is greater than 0, that means it's always going to approach 0. So what if it's a negative infinity? Then you would just put L on the bottom, or in your classes you've been taught to put A on the bottom. So you would just do the same thing. You would solve the integral first and then use the limit, and then use that equation or that answer that you get from solving the integral to find the limit. And then if you have from negative to positive, as we talked about, you break it up, solve each one separately, and then find the limit of each part, and then you would add those together to find whether the function converges or diverges, right? So if the if you get a number at the very end, that means it's convergent. If you get a infinity or negative infinity, that means it's divergent. So this is basically what this talks about, that we just talked about, like how to solve and everything. And then because of time, we will not actually be going over examples here, but instead we will go over the questions in the practice problems that will talk about how to solve these improper integrals. So moving on to partial derivatives of first and second order. So your partial derivative of a function is c equals fxy with respect to variable x. And it is denoted this way. That is c over x. So basically you have to find, once you find your first order partial derivatives, which is your fx and fy, and then you would move on to finding your partial derivatives of that. So it would be fxx and then fyy, and then it would be fxy and fyx. So so if you're trying to find, let's say you have your equation, right, your function, and you're trying to find fx, that means you're trying to keep your y constant, and then you're trying to take the partial derivative of x. So treat y as if it's a number. And then if you're doing fy and you're trying to find the partial derivative of y, you want to treat x as a number. And then to find fxx, you will use your partial derivative of fx, right? So you'll use fx to find xx, where you will find the partial derivative of x. And then for fyy, you'll do the same thing, but with fy. And then for fxy, you will use the partial derivative of fx, and then you will keep x constant and treat y as the variable. And then if you're doing fyx, you will do it the other way around. Something to remember is that your your fxy and your fyx have to equal each other. So this just kind of talks about a few reminders. So if you're differentiating with respect to variable x, treat y as a constant, and then just go through and like differentiate. And then if you're doing it with respect to y, then treat x as a constant. And then we can apply differentiation formulas multiple times to get the higher order partial derivatives. So obviously for this course, we'll just be doing like second order partial derivatives, so you don't have to worry about the rest. Okay, something to keep in mind throughout this exam is that you're not getting confused between integrating and differentiating. For example, with improper integrals here, you're differentiating. You're integrating, right? You're trying to find the integral of a function. But when you're trying to find derivative, you're not integrating. So that is something that you want to keep in mind, is that you are constantly having to switch between finding the integral and then finding the derivative, and you don't want to confuse both. So make sure you learn the differences between both of those and the formulas and everything, because you don't want to be asked to differentiate 1 over x and then put that as ln x, because that's the integral of 1 over x is ln x. And then, also the whole time, if you have any questions, feel free to put them in the chat. And then the next thing we'll talk about is unconstrained optimization. So this is basically where you have your saddle points, your maximum minimum. So the first thing that you would start by doing is finding the critical points. You will find the domain first. This is a given for any time you're trying to find critical points, you always want to find the domain first. And then to find the critical points, what you need to do is you need to first find fx, fy, fxx, fyy, and fxy. So to find your critical points, you will set your first order partial derivative with respect to x, your first order partial derivative with respect to y, and then you will solve the system involving the partial derivatives, right? So you want to set them equal to 0, and then you will just go ahead and solve and see what your critical points are. And then you will go ahead and set up this equation. So you want to remember this formula right here, that your second order partial derivative with respect to x times your second order partial derivative with respect to y subtracted from your fxy squared. And then your x and your y here is basically going to be your critical points that you're going to plug in. After you find the critical points, make sure it is within the domain of the function. If you see that your critical points are not within the domain of the function, that means they don't exist on the graph. So there's not going to be a minimum or a maximum for it. So now let's come down here and then see that once you start plugging it into the function, you will then see, okay, when I plug it in to the discriminant, you will see that if it's greater than 0, then you want to plug in those critical points into your second partial derivative with respect to x, and if it's less than 0, then you will determine that it's a maximum. Let's say it's greater than 0 with the discriminant, greater than 0 with the second order partial derivative with respect to x, then it's a relative minimum. But if the discriminant is less than 0, then it's a saddle point. And then if it's equal to 0, then the test has failed. So those are just like a few things to keep in mind, and these are the steps that you will use to solve unconstrained optimization. Let's move on to constrained optimization, and this is where you are given a constraint and you need to use that to solve the problem. So the first thing that you will do is you will set up your constraint equation. So you want to rewrite your constraint in the standard form, g of xy is equal to 0. And after you write your constraint, you will go ahead and construct the Lagrange function, which is basically this right here with fxy minus lambda gxy. And your gxy here is your constraint. And then you will go ahead and find fx, fy, and f lambda. And then you'll set each one of them equal to 0, and then you will solve the fx and the fy for lambda, and then you will set those values equal to each other, and then you will use this and those two as a system of equations to solve the problem. And then you will be given you will find the critical point basically. So what you want to do is, how are you going to find if it's a maximum or a minimum? Like, let's say the question does not say, it just says find the relative extrema. One thing that you want to do is you want to find a point closer that satisfies the constraint, and then you want to plug those numbers into the function. So let's say you plug in the critical point that you found, and then you found a point closer, and you plug both of those into the function, and your critical point is less than your function, less than your closer point, then it's a relative minimum. But if it's greater than your closer point, then it's a relative maximum. So you want to check every single point that you get from the system of equations that you solve here by finding a closer point and trying to see whether it's a relative minimum or a maximum. And you also want to make sure that it satisfies the constraint. Okay, so next up we have total differentials. So with total differentials, we are given the function dz is equal to fx and then fy. So how you would find d of x right here is you will take your given x value in the function and then you will subtract it from the whole number. So like let's say the point that you were given is like 4.96 square plus 12.06 square. The whole thing is square rooted. Then you will do 4.96 minus 5. So do you see how 4.96 is your given x and your whole number is 5? So you round up or you round down based on the number. And then whatever difference you get is basically your dx. And then you would do the same thing for dy. So for your dy, it would be 12.06 minus 12, which is equal to 0.06. And then you would use that to plug it into the equation here. So you just set your equation up into dz is equal to 5, and then your 0.4, and then 12, your 0.6. So, and then you would go ahead and solve it. And when it's talking about dw, it just means that there's 3 different variables instead of 2, right? So if you were to use total differentials to approximate, then you would first calculate dz, and then you will use the function and then set it equal to fxy plus dz, and then you would just solve that to find your approximation. And this will make more sense once we're working through the problems. Next up, moving on to separable differential equations. So first, let's see what a differential equation is. A differential equation is a relationship between dy and dx, right? So these are a few examples of differential equations. So on this exam, there's only separable differential equations, but then on your next exam you will learn, or after the exam you will learn about first order differential equations that you don't have to worry about for now. So talking about the differential equations, so there's something called the initial condition, which you will use to find your initial value problem. So once you solve through your differential equation, you will then get a general solution. And then if you need to find a particular solution, you'd use this initial condition, which is y of x0 equals y0. And you'd plug that into what you get here into the general solution, and then you'll get a particular solution. So basically when you solve your general solution, you'll want to add a plus c at the end. So moving on to like implicit solutions versus explicit solutions. So an implicit solution is when it's not like completely solved. Like you still have like an equation on the left and an equation on the right. The y is not completely isolated on the left with everything moved to the right. For example, like ln of y is equal to your answer. That's an implicit solution. An explicit solution is when there's just y on the left and everything else is moved to the right of the equal sign. So it would just be y equals ln of something, something, something. That is an explicit solution. So moving on to what makes an equation separable or not. So separable differential equations are when you see something that's like multiply and you can move it around easily. So for example, let's look at the one here. So it's just going to be dy divided by gy and then fx times dx. So it was just easy to first to move it. So you see you can separate the variables using quality, right? And then you can just integrate both sides, and then you will just solve it as it is, and then you want to make sure that you're adding plus c. So you will just solve it like it's any other equation, and then you'll just add plus c. So do you see this is a general solution because y is not completely isolated from the rest of it. And then if you're given an initial condition, then you can use that initial condition to solve for c by plugging these two x and y values in here and then computing what c is going to be, and then you can rewrite your solution. Remember, that will be a particular solution, and general solution and particular solution are two different things from implicit versus explicit solution. So make sure not to get those confused. And then after that, you can like go ahead and solve it to the point where you want an explicit or implicit solution. But those are just a few general ways to solve that. Another thing that's going to be on your exam, as we're talking about, is like the double integral, right? So you want to start, so something that's going to be confused up, there are some times when you can just switch the dx and the dy without having to graph the whole thing and change your bounds. So let's say there's no inner bounds or just normal numbers, then you never have to graph it. You can just switch your dx and dy. But if your bounds are different, if your bounds are like equations or something, like let's say it's from 0 to 4 and then x squared to 5, then you need to graph it and figure out what your new bounds will be, and then you will come up with your new bounds. You can't just like switch x and dy and dx and then solve it. But basically you will just solve double integrals just like you would solve integrals, and you would just need to remember when it's fixed numbers you cannot switch integrals, but when there's a variable you can switch it. And then make sure that if you're solving indefinite double integrals, when to add plus c of y or when to add plus c of x. So when you're doing the integral with respect to dx, then you would add plus c of y at the end. But then if you're doing if you're integrating with respect to dy, then you would do plus c of x at the very end. But yeah, those are just like the only things that I have for you guys today. I'm gonna go ahead and stop sharing.
Okay, cool. Do you mind like going over the changing the integral things? The bonus question you were talking about?
Hi guys, I'm Luke. Let's first try to think of an example of where we would have to switch the bounds on a double integral. So we're integrating, well, first let's start with like a rectangle, some function of two variables. Okay. So what does this information encode to us? This information is our region of integration is something in the xy plane, where a is less than or equal to x is less than or equal to b, and y is in between c and d. So this is just a rectangle. We can draw it. I recommend drawing a picture for a lot of this multivariable calculus. So this is our region. And this is no problem to switch the order of integration. So like, we always treat these double integrals like there's an inner and there's an outer, inner and outer. And so switching these, we could just call this I guess. So I is also equal to, if we want to now write it as, I'm going to leave the bounds off for now, and I'm just going to switch the differentials and then fill in what's going to happen. Well, if we just switch the differentials, I mean, y is still going from c to d, and x is still going from a to b, so this really doesn't change anything. We just put c to d right here, and we put a to b. But, I mean, I asked what these bounds, what this information encodes. I kind of neglected to ask, what does this information encode? What does this information encode? So to answer that, I make an appeal to a stick figure. So dy dx, I call these vertical cross sections. And then dx dy I call horizontal cross sections. And we can realize what these mean with the stick figure. So dx dy is horizontal cross sections. It's like this. And then it's always like the left side is lower than the right side. So if I draw a stick figure right here, we can see that his floor, if he was living in a house, if this box was his house, then the floor he's standing on is x equals a. So this is always like the floor of the man's house. And then this top part is b. It's a simple function, right? I mean, it could be any function. Like I could have made it like a curvy line in between them, and then in that case, his roof would be considered a different function than x equals b. And then and then we can look at what a vertical cross section is. So we have the same region, just we're going to look at it from a different perspective. We have a to b, c to d. So vertical cross sections, that just means I draw a vertical line and I have a person, right? The bottom is always smaller than the top, so his floor is the bottom, and the top is his roof. So now this function that is his floor is now a function of is y as a function of x. So it's like y equals something, and it's y equals c. So it's still the floor over here. And then his roof, well, that's just d. And then we look at the outermost integral, so like the dx in this case. The dx in this case like travels straight along an interval, so you don't have to think of any function for that. These outermost will always just be numbers. It's like we knock it down sort of like a level of complexity each time we evaluate an integral. Like there on the innermost integral, there could be a function of, as you know, so many variables, like probably n-1 variables, like the number of variables we have, and subtracting one from that. So if we have 3 variables, then the innermost integral can be at most like a function of 2 variables. for the bounds, and then as we peel that off, then the result is a double integral with here, I'll show you what I'm talking about. I'll show you exactly what I'm talking about. dz, dy, dx. So like if we have some function in here, f of x, y, z, then this dz integral right here can be like f, or I can't use f. So let's use g1 of function of x and y. This is g2 function x and y. And then the next one, this integral, this is dy, but this is y as a function of x only. And then we knock it down one more level of complexity, right? We had 2 variables, we had 1 variable, now we have 0 variables. This is just x on an interval, a to b. Okay? So this works. So now that we have the vertical and horizontal cross sections, does that make sense? First of all, does anyone? Does anyone have any questions over? I mean, the only question I could, foresee was like, what is the point of this? Well, we can get. Well, I'll answer that one when we change this region from a rectangle to something else, a more general region. Okay, so now let's look at an example. E to the x squared dx dy from y to let's say 100, and then dy is going from 0. No, we can make this smaller. Let's make it 10. Zero to 10. So it's just this triangle is what this information encodes, this triangle, this region R. So this is what we're integrating over. Now it's a triangle. It's a little bit more complicated than a rectangle. So this is, wait, hold on, did I do this right? dx. Let me change these. 0 to, okay, this is a little bit more correct. 0 to y. Okay, and then this information, yeah, this is good now. And then this guy, what does this say? This is horizontal cross section. So that means I draw horizontal, and then we can draw our stick figure, and we can see his floor is x equals 0. That's right here. And we can see his roof is x equals y. That's right here. It's just a line. So this is roof, floor, and then of course y is just 2 numbers. going from 0 to 10. And so now we're going to write this. Well, first, I deviously picked this function to be the integrand, because if you try to evaluate this as it is, you can't do it. So go ahead and try to integrate this and find that is impossible with the current horizontal cross sections. He doesn't know how to integrate it, so he's sad. And he shouldn't be sad that he doesn't know how to integrate this function in particular. He should not be sad that he doesn't know how to integrate this, because no one can do it. I mean, there's special integrals involving this integral, but as far as finding an explicit formula for the antiderivative, we don't have one. Maybe we have something with series, which is not covered in this class, but we can't find an antiderivative in terms of elementary functions, and elementary functions are just things that we've been dealing with in this class. Functions like e and log and polynomials. These are all elementary functions, or radicals. So this is not solvable. But if we change, then try dy dx. So we're gonna change the bounds. Well, first let's just write everything. We're gonna change to dy dx. So yeah, my suggestion is then just write it out first, and then worry about the bounds once you have the differentials in order. And so now we have the same region. We're just looking at it from a different perspective. So if I now do vertical cross sections, what is my floor for my dude if I draw him upright? Well, this is his floor. But we just we invert the function, or we solve for the other variable. So this was dx. So like dx corresponds to x equals y, or x equals a, x equals b. And so this will be like y equals a and y equals b. And then in a similar fashion, x equals. So his floor is just y equals x. Y equals x is x equals y. So that's his floor. And then his roof is just the constant function 10. Okay, and the resulting single variable integral will be evaluated from how far does he walk? What's his path in x? So he travels from 0, and then this comes all the way down to we require 10. Because that's just the intersection of y equals 10 with y equals x. So both of these, that just means x equals 10. So you might have to solve something like that, so be aware. So we got 0 to 10. And now the good thing is for this, is we can integrate this inner one like magic. We couldn't do it before. But now this is super simple. Why is this super simple? Someone tell me how to integrate this. Someone tell me how to integrate from x to 10 e to the x squared dy. What is this? You just told me the antiderivative. Remember, x is being kept constant.
So y ex squared.
Yeah. Y times ex squared. Yeah. And then we evaluate, of course. Oh, does this work? Maybe I thought of a foolish problem. So then,
Yeah, then plug x in for the y, and you can use u substitution after that.
I'm worried about, we'll have 10 e to the x squared minus x e to the x squared.
Oh.
Yes, man. It was cool in theory, right? I would have to, I was trying to think of that on the fly, and apparently I performed a blunder. So, but I mean, you can evaluate one of these, right? You can evaluate the right one, just like our friend said. You just use u substitution right here. You could actually solve this one. I would need to think of a way to, it would need to cancel with something. But I mean, we can just proceed as if, so we get the process down. Oh, you know what? If I did the lower triangle, if I change the bounds, if I change the region, then we could get this term to cancel. If it was just like this lower triangle, actually, yeah. So if it was actually this region, then this would be from y equals 0 to y equals x, and then x equals 0 to 10, and then this would work. Okay, so let's try this one. So then this is, yeah, this is of course the integral 0 to 10. This inner one is like the same for the antiderivative. I mean, we didn't change anything with the function, so y e x squared. Then we can evaluate this from 0 to x, and then we can put a dx. And then this is 0 to 10 x e x squared minus 0 e x squared dx. Ah, yes. So 0 to 10 x e x squared dx. And then the person who told me earlier what method, what technique of integration we should use to solve this integral, don't answer this question. But someone else tell me, what method do we use to solve this integral? What technique? Anyone? Yeah, I think it was the last exam. I don't know. It might have been from math 1325. Well, that is, granted, everyone is paying attention right now. Or assuming everyone's paying attention. Does no one know? Or is
Would it be integration by parts?
let me see if you could use that. That's not my go-to, but I don't know if that wouldn't work because it is technically a product of two functions. So like if we pick u is we do liat or ilate. So algebraic u is x, du would be dx, dv ex squared dx. Oh, see, yeah, we can't use this because we can't integrate this one. It's good to know when you can't when you know you have something you can't handle, right? And this is one of those cases. Yeah, we can't use integration by parts here because we would need to integrate e to the x squared dx to get v. That cut out for a second. Okay. So there's actually an easier technique to use. So what's the technique we learned before integration by parts? I think there was only one before integration by parts. So let's think. So we have, I'll list all of them. I'll list all the techniques, and you can choose. So techniques. So we have integration by parts. I'll write them in order. We have u sub, integration by parts. I think we have partial fraction decomposition. And then of course like 0 is like direct. Yeah, so I think these are the only 4 ways we can do it in this class. There's no fraction. We already know it's not integration by parts. It doesn't appear we can do any sort of like directly. So it has to be u sub. And then you can also tell it's u sub in a more sophisticated way than process of elimination. You can tell this is u substitution because there is a function being composed, which is x squared, and x squared's derivative appears in the integrand also, almost, up to multiplication by a constant, which is okay. So we have a function that's being composed, and then we have its derivative in our integrand. So this is du over 2 equals x dx. So if I choose u to be x squared, this means that x dx is du over 2. We have an x dx in our integral. I mean, up to ordering. We can just reorder it, and then it'll be exactly like this. So that takes care of our x dx. And then our e to the x squared would just be e to the u. And I know how to integrate e to the u. So if you choose, I usually do, to make a table. X is going from 0 to 10. U is going from 0 to 100. Okay. Then this integral turns into the integral from 0 to 100 with the 1/2 e to the u du. So what is the antiderivative of exponential u with respect to u?
Itself.
Itself. Yep. Okay, so then this is 1/2 e to the 100. We can put it in parentheses, minus e to the 0, which is 1/2 e to the 100 minus 1. So let's scroll out to get an overview. Okay. So this rectangular region that we started with is preliminary to understanding more general regions. So we always, when thinking about these multiple integrals, we'll do it in a box, whatever dimensional box we're in. This has two variables, so it's a two-dimensional box. And in one dimensions, like if we have a to b f of x dx, well, this a to b this encodes, this is on the interval a to b. Well, this is a one-dimensional box. And then, yeah, and then if we have, two integrals, then it's a one-dimensional box times a one-dimensional box, which is a two-dimensional box. So yeah, well, what I'm saying is there's a strict analogy to single variable calculus. All this stuff is literally is the same. Yeah, I mean, like what were we doing in single variable calculus? What were we doing in Math 23 or 1326? Well, we were doing derivatives and integrals on functions of single variables, and getting approximations of things with tangent lines, and finding maximum and minimum either on an unconstrained domain or a constrained domain. Let's see, what else were we doing? We were evaluating single area and single variable integrals and to determine area. Now we're just doing this on an infinite spot, right? This is improper integration. That's still single variable calculus, so I'll leave that one out. But like this find all partial derivatives, like you could just call this, a calculus 1 problem, and then take out a single variable and say find the derivative. This unconstrained optimization, this is relative max and mins. Those are things on. Remember the second derivative test. The second derivative test is well, first of all, the critical points are where the derivatives are 0. That's the same as in calculus 1. So, and then classifying them. Well, to classify them, you need the discriminant. Well, the discriminant is really, right, d equals fxx squared fyy squared minus, you need to know this for the exam, right? This guy is squared because mixed partials are equal. fxy is fyx always in this class, always. Remember this. So really this discriminant is actually fxx squared fyy squared minus fxy fyx. Okay, so this is multivariate second derivative test. Like before, in single variable calculus, we would take the second derivative at a critical point, and you would look to see if it's less than, greater than, or equal to 0. And we're doing the same thing with the discriminant, right? We determine if it's greater than, if it's less than. If it's 0, it's inconclusive. But if it's greater than 0, then we have potential for extrema. If it's less than 0, it's definitely a saddle point. So this is the same thing as in calculus 1 when we were just doing the second derivative and determining the sign of that. Now we have a bigger tool, right? We have a bigger tool now. And let me tell you, this bigger tool covers what we know about single variable functions. So it's actually just a generalization of this single variable case. Like all of this stuff, it's just a generalization. Like the single variable case still lives and works in this multivariate system. And it goes higher than 2 dimensions, you know. So that's just me, you know, trying to give some, like connect the dots here. We're doing the same thing that we were doing, you know, last semester. We're just doing it with two letters now. All right, that's basically it. So evaluate the double integral right here. Like this would give me some volume potentially if it was all above the xy plane. And you know, an analogous calculus 1 problem would just be evaluate the single integral to find area. Approximate using total differentials. This is an analogy to single variable calculus linearization. Linearization was when we had some like curvy thing and we know its value at some point. Maybe we know its value like right here. This is a bad picture to do it on. Yeah. So let's say we know this point. This is a nice number to compute. But we don't know the one near it. We don't know how quickly it's changing over, you know, we don't know what the value of f is right here. We don't know f right here, but we know f at the black spot. So what we're going to do is we just draw a tangent line. And then we use the tangent line to approximate the value of the function. So we look at this value and we say, okay, well, this is close to, let me zoom in. Yeah, we say like this is close enough. If we stay near this point, like if we're within some distance of this like x0, then like when we plug in x to our linearization, we get things that are close to f of x. So L of x is approximately f of x near x naught. And remember, the formula for L of x involved the derivative, right? It had f x0. It's just a tangent line at the point. So it's plus f prime x0 times x minus x0. So like you don't need to know this right now, but this is what we're doing in multivariable now. Like this approximate using differentials. So if we were using a straight line for the linearization in single variable, then what object will we use to do linearization in in 2 dimensions, or I guess 3 rather? What object will we use to do this linearization instead of a line? Anyone want to take a guess? So it turns out we're going to use, instead of tangent lines, we'll use tangent planes. And it turns out that your differential formula, dz equals f x. This is the partial of f with respect to x of x0, y0, dx plus fy x0, y0, dy. So if we change all the d, the dz, the dx, the dy, if we change that to what it is, they're approximately z minus z0. Dx is approximately, well, no, actually dx is exactly, we know what dx is. It's exactly x minus x0. And then dy is y minus y0. So if we then convert this, like we have z equals z0 plus fx, x minus x naught plus fy, y minus y naught. Oops. This is actually the tangent. This is the formula for tangent plane. This will give you a tangent plane. So, and I know you guys don't really cover that, but it's literally what the total differential is. And then separable differential equations. I will say that's probably the one topic that doesn't have a single variable calculus analogy. Because differential equations is like its own field. Yeah, it's kind of separate from calculus. Okay, so I guess we can get started on these questions now. Oh yeah, well, I haven't really finished. I kind of got sidetracked recapping. So yeah, yeah, we looked at these horizontal and vertical cross sections, and then we just applied it to more general regions. These lines don't have to be straight, like the region on R. Like R could look like this even. Yeah, or something like that. It could be a weird shape. It could be like a circle. It won't be a circle in this class, but because you would need sine and cosine for that. But it could be like, yeah, it could be a whole circle. These are all options for R, or for the region. So you're just looking at what you got and drawing a picture, really. Draw the little stick figure. Draw what, first write your differentials, and then worry about the bounds. Don't try to, worry about the bounds before you write the differentials, because the differentials are like a guide to, where I'm going to put this bound, where am I going to put this bound, what orders does it go in, so I need to write that first. And yeah, and we were able to solve this otherwise impossible integral by changing the dy and the dx. Okay, so which one do you guys have a preference as to what you see first?
No, I don't think so.
Okay, let's do let's do 4, the constrained optimization. No, let's do 3 first. We'll do 3. So find the critical points of the function and classify each critical point as a relative max, a relative min, or a saddle point. So critical points, those are cut points. I think that's what they call them in Math 1326. So critical points, cut points mean the same thing. Critical points occur where f partial x equals 0 and partial f partial y equals 0 at the same time. So if you know what this means, this is the same thing as this, where if you don't know what the gradient of f is, this is just a vector of partial derivatives. So it's a list of the partial derivatives. So we can use it like that, and just say this equals a 0 vector. So like you set each component equal to 0. You set each component equal to 0. This one equals this one. This one equals this one at the same time. And then, yeah, and so wherever the gradient is 0 is where the critical points occur. So first we have to find the partial derivatives, right? We could just say gradient f equals, and then partial f partial x would be negative 3y plus 3x squared. Partial f partial y, 3x minus 3y squared. And then we equate this to 0. And we solve for which x and y makes this happen. So we have 3x squared, 3y squared is 0. 3y squared minus 3x squared is 0. So this tells us that x squared minus y is 0. And y squared minus x is 0. So this one tells us that y is equal to x squared. We know what that is. That's just a parabola. And this one is telling us x equals y squared. This one is also a parabola, just in the other direction. And so we're going to look at the intersection of these two parabolas. Is parabolas the correct plural for parabola? I don't know. Anyways, we have one parabola looking similar to this. And another parabola. So does x equals y squared? Does that open to the left or to the right? Can anyone tell me this? I guess the most friendly way to, so if you guys may have never seen this before, and the most friendly way to introduce this would just be to take the square root on both sides. So y equals plus or minus the square root of x. Well, I know what the square root of x looks like, and then I know what negative the square root of x looks like. The square root of x looks like this, and then the negative is just flipped. So that's cool. We have two intersection points, the origin and also this one. Okay? This is where the gradient is 0. Remember, this is not integration or anything. This is derivatives. So don't look at the region. Just look at the intersection points. Okay? So then so then we have two critical points. We have zero, 0, and what is this point up here, guys? What is this upper one? Someone tell me. What is this upper point?
Is it 1, 1?
Yes. Yep. Okay. And then so this is the answer to the first part. Now the second part, classify. Okay. So what does that mean? That this means we have a list of stuff to remember. If you can remember this, you'll do very nicely on this question. So if d is greater than 0 and fxx is less than 0, then we have a max. If d is greater than 0 and fxx is greater than 0, then we have a min. If d is less than 0, then we have a saddle point. If d equals 0, inconclusive. Okay. So really, you only have to remember 3 things. Because this equals 0 will only happen in this class if you have done it wrong. They won't give you anything where d is 0. But it would occur if fxy does not equal fyx. So this happens when fxy does not equal fyx. But earlier we said that these are always equal. Well, that's another one of those things. They're always equal in this class. So if d is 0, then fxy does not equal fyx. And then this would happen if the second partial derivative were not continuous. If we had it would be like if a function is changing so bad that we can take one derivative, okay, but then we take the second derivative, and then when we take the second derivative, we get a function that's not even continuous. So we can only differentiate twice before it kind of like blows up on us. And it's yeah, you can construct some examples like this. I think the only way I've seen them really defined is as a piecewise function. So like something that is normally like doesn't really work at the origin. So so like something like This is I don't know if this would work, but this is like x squared y over x squared plus y squared, and then you define it to be 0 at the origin. So for all x, y, and r2, oh, you don't know what this means. So for all for x, y not equal to 0, 0. For x, y exactly only equal to 0, 0. So when you define the function in this way, you have the possibility that fxy does not equal fyx. But you guys don't have to worry about that. We're just doing continuous second partials. So this fxy equals fyx. This is actually something called Clairaut's theorem. I have to look up the spelling. Clairaut. How do you spell route in French? So this is Clairaut's theorem. He has a gravity theorem, but this is the mixed partials equality. Yeah. So so this is true provided fxy and fyx are continuous. And we don't have to worry about anything other than this right now, or probably ever. Yeah, but what is this discriminant? I didn't even define it. So D equals fxx fyy minus fxy squared. Okay, everyone listening right now, has anyone taken the linear programming class? I think that's required for business.
No, I haven't.
Is that something that sounds familiar though? Where
I don't believe so.
No.
you guys don't have to take that class? Okay. Well, I would make an appeal to linear algebra right now, but I feel like it wouldn't have any value at this point. As to where this D comes from, D equals fxx fyy minus fxy squared. So instead of making an appeal to algebra, I will make an appeal to geometry. The geometry of these curves, what this fxx, fyy, fxy, what these actually mean. Because like right now, it's just like a set of rules I have to remember, right? And it kind of doesn't make any sense. But I mean, what do we know about, this calculus so far is, like these analogies we can make back and forth from single variable to multivariable. So we'll work on that. So first, the second derivative test. So if C is a critical point and f double prime of C is greater than 0, then this tells us, so if f prime of C is 0 and f double prime of C is greater than 0, then is this a max or a min? You may not know from single variable calculus, but just look right here. if the second derivative is greater than 0, provided this d is greater than 0, but we don't have a d in this single variable case, then it's a min. Okay, so like really, I don't remember it like this. I remember it like a picture. So I know I have a horizontal tangent line somewhere, right? Because f primacy is 0, and then I also know it's always concave up. Remember, the second derivative gives us concavity of the function. So a second derivative being positive in some interval means that the function is concave up in that interval. Concave up just means it's opening upward like a soup bowl. So, and then that fact paired with the derivative, the first derivative is 0 at some point. This is the only way to draw this shape. And then, of course, I can see there's a minimum value right here. And this is the horizontal tangent line. We can tell it's always concave up, so this is the correct picture. Okay. But anyways, so let's look at if d is greater than 0. If d is greater than 0, then fxx fyy minus fxy squared is greater than 0. That's just what d is. Then I'm going to add fxy squared to both sides of this equation, or this inequality. We have fxx fyy is greater than fxy squared. Okay. And then we have a okay, yeah. So d is greater than 0, but what if fxx is what if this is less than 0? Then what is fyy? Is this if fxx is less than 0, then is fyy greater than or less than 0? For this whole thing to be greater than 0. So if this is negative and this product is greater than 0, then fyy would have to also be less than 0, because two negatives multiplied together make a positive. If fyy were greater than 0, then this product would be negative, and then we would have a contradiction with the fact that it's greater than 0. So, so if d is greater than 0 and fxx is greater than 0, then fyy is also, or if fxx is less than 0, excuse me, then we have 3. 3 is fyy is less than 0. So we have the second partial derivative in both x and y is less than 0. So now we can look at like what would that mean? So that would mean that like at some fixed y value, we have a curve so at some fixed y value down here, we have some curve on the surface that like projects, like it's the mapping of a curve onto the surface. And then this curve we can take, it's a function of x, so we can take a second partial derivative of it. We can take like the second derivative with respect to x of this curve, and it's less than 0. It's less than 0. So, and we also know there's a point that equals 0. That this at this point it equals the first derivative equals 0. So then this means that the only way to draw this red curve would be like this. And then the only way to draw this curve similarly, right? I mean, we fix an x value, we trace it over here, and then we look at its image on the surface. We know that the first derivative is 0 at some point. And then we also know that it's concave downward. So the only way to draw it is like this. So we're looking at the surface from two perspectives. We're looking at it if we fix y and if we fix x. And we can see in both these cases, in both directions, there's a maximum. So then surely if d is greater than 0 and fxx is less than 0, then by this geometric argument, we have a relative maximum. Yeah, in a similar manner, you can do the minimum. And then saddle point, I would have to think about that one. And I don't want to spend more time on this than we have to. But I kind of want to I wanted to give some rhyme and reason to it, you know. Anyways, we can continue with this problem. We have to classify the critical points 0, 0, and 1, 1. So that means we need second partial derivatives. So the first partials was just gradient f right here. So then fxx would be if I took this guy and then took the x derivative of him, which is just 6x. fxy is fyx is, well, I can take this guy again and just take the derivative with respect to y now. And so now it's -3. And then I could also, alternatively, I could have just taken fy. I could have just taken this guy and take the x derivative, and it's also -3. And that always happens. So fyy would be just -6y. And then I can plug this into the formula. Fxx fyy minus fxy squared. So then I'll do d of xy is -36 xy minus 9. So this is -9 times 4xy plus 1. So this is d of xy. It's a function. So d of 0, 0 would be -9 is less than 0. D of 1, 1 would be 9 times 5 is -45. That's kind of, oh man, that's not fun. So they're both saddle points. I guess this guy doesn't have any. Yeah, that makes sense. It's cubic. Okay. Well, that's disappointing. Maybe if it was like the exam question, that would be like a good thing. But as for like an example to show people, since they're both less than 0, that means we have the work's done, right? We can look back at our classification theorem. If D is less than 0, then we don't have to consider anything else. It's just a saddle point. Unless I did something wrong. So if anyone sees an error, please let me know. But this looks right to me. Okay, so then so then 0, 0 and 1, 1 are saddle points. I'm gonna show y'all a surface. So this is just an online, it's called math3d.org. So we can see at 0, 0, that's this point right here. We can see this is definitely a saddle point because from one direction it looks like a minimum. But the other direction, how do we do this? The other direction, it looks like a maximum. So minimum, maximum. So it's a saddle point. It's where someone would sit. But apparently this 1, 1 is a maximum. So we can add a point 1, 1. Oh. Well, I think I messed this up, actually. Hey, did anyone check my work on the partial derivatives? I'm sorry, y'all. Let's go back and look at. See, that's the good thing about graphing it on this calculator is now we can see. Oh, this looks wrong. So we should have one saddle point and one maximum. So it's probably. Oh, it was right here. I see it. This should be a positive right here. And so this is x equals negative y squared. So then that changes our critical point. Changes this curve. And then now it's negative y squared, so it's over here. So then we still have 0, 0, and then that turned out to be a saddle point. And then this negative 1, positive 1 is a critical point. And so we just do d of negative 1, positive 1. We determine the sign. So this is 6, negative 1, well, negative 6, negative 1, positive 1, minus 9, plus 9. So d of negative 1, 1 is, positive 36.
minus 9. 36 minus 9 is 27, is greater than 0. So d of negative 1, 1 is greater than 0. So then all we need to do is determine the sign of fxx. So if fxx is equal to 6x, then what is fxx of negative 1? This is negative 6, is less than 0. So, therefore, there's a maximum. If d is greater than 0 and fxx is less than 0, then it's a maximum, according to this first one right here. So then we're done. Yeah, that was this problem. We classified. Let me change this up. Negative 1. Oops. This is a max. And this is a saddle. Okay. So now that we have done unconstrained, we will look at constrained. So constrained, we need the method of Lagrange multipliers. Constrained optimization. So like another analogy to single variable calculus, this is when we had like, this is absolute max min of a function on a closed interval. This is analogy 2. So now instead of a closed interval, we have a closed region in R2. Well, it's subject to a line. So let me think about this. Let me put a question mark right here because I'm not sure if I can actually make that one. But okay, here's what we got going on. We have f of x, y being this. This is actually just a paraboloid. It's a parabola as a surface. And then what is this? X plus y equals 8. This is a line. So we have some paraboloid. And then we have y equals 8 minus x. So it will look like this. And then we look at the image of this curve on the surface, and it would look something like this, going up forever. And we're going to find the max and min on, on this this image curve on the paraboloid. So we can already tell right now from this picture that there's going to be a minimum and no maximum. So well, we have f x y lambda equals f x y, was it minus g minus lambda g xy, and then we take some derivatives. Fx is fx minus lambda gx. Fy is fy minus lambda gy f lambda equals negative g. Okay? So first, I mean, we can just take the gradient of f. That's just partial f, partial x. So partial f, partial x, 2x minus y. Partial f, partial y for y minus x. G, gradient g is, well, g is just x plus y equals 8, in some degree. So this is just 1 and 1. So we'll call this equation 1. We'll call this equation 2. We'll call this equation 3. So 1 means that that 2x minus y minus lambda. You set these equal to 0. So I guess you say 1 equals 0, 2 equals 0, 2 0. So this means that lambda is 2x minus y. And then 2 implies that lambda equals 4y minus x. And then uh, 3 implies x plus y equals 8. So does everyone agree that this is true? Is this true? Is anyone not sold on this? Okay, yeah, and this is obviously true. This is called reflexive. So not every equals, not every quote unquote equals has this reflexive property, but the equal sign that we're used to, that does have reflexive property, and we're used to that from using it since first grade. So we know that if x equals y, then y equals x, or whatever. So lambda equals, oh no, wait, I'm sorry. We know that that second one was symmetric. So what I meant to say is, we know that anything equals itself. That's always true. So then we can set these two equations equal to each other, so that we eliminate lambda. So now we have 2x minus y equals 4y minus x. So I can add y, add x, 3x equals 5y, y equals 3 over 5x. Then we can plug this into 3, equation 3 right here. We have 3 over 5x. We have x plus 3 over 5x equals 8. 5 over 5, 8 over 5x equals 8. X equals 8 times 5 over 8 is just 5. And so this means y is equal to 3. Okay. So then 5, 3. Do we say it's a critical point? Or do we say it's a max or a min? We say it's an extrema. Yeah, this is an extrema. We don't know which one yet. Okay, how do we find out which one it is? How do we find out? Is it a maximum or a minimum? Can you guys hear me?
Yeah, we can hear you.
Okay. Oh, okay. So, Gori talked about it. I hope I said your name right. But she talked about what to do to determine if it's a maximum or a minimum during the PowerPoint. So,
You'd
if
have
we
to take
remember
neighborhood analysis.
neighborhood analysis, I've never heard of that before, but that sounds right. Yeah, that's awesome. I like that. I like that terminology. Neighborhood analysis. Yeah. But unfortunately, guys, I'm gonna be super lazy and make an appeal to geometry, which I did at the beginning of the problem, if you guys remember. Neighborhood analysis, man, that's good. Yeah, so this picture, we know it's a paraboloid. And so as we get further away from the origin, so as x, y, well, as the square root x squared plus y squared goes to infinity, f of xy also goes to infinity. And so so then the reciprocal is true, that like what if this is approaching if like this is just distance from the origin. So this is saying as we get further away from the origin, as we're getting infinite distance away from the origin, f of x is also blowing up. And then so as the like corollary to that, if we get closer to the origin, now if this approaches 0, then fxy also approaches 0. Okay. And so so then it's just a matter of minimizing the distance of the line with the origin. Like, where is this line closest to the origin? So then that would be a single variable calculus problem at that point. But apparently it occurs at 5, 3. And then since this is close to the origin, it implies that our function f is minimized. So that's what I would say about that. I don't know if that's super rigorous, but of course, on your exam, you should do the neighborhood analysis to determine. And that all that means is like, okay, so we take I would stay on the line. I would stay on x plus y equals 8. But we could do like 4, 2. We could do f of 4, 2. And then we compare this to f of 5, 3. So f of 5, 3 would be, oh, I don't want to do that. 25 plus 18. Oops. Minus x times y minus 15. Oh, that's not too bad. 3, so 28. And then this one is 16 plus 8 minus. Oh, what the heck? Why did I get a smaller number? Gosh darn it. This is 16, which is smaller. And I was claiming that it was a minimum. And so f of 5, 3 would have to be smaller than anything.
Luke, I'm so sorry to cut you off right there, but we're we're
Yes,
approaching
okay.
the end of time. So thank you everyone for joining. You can find like all the resources that we like went over, the slides, the work problems, and the answers to those on the UTT Peer Tutoring YouTube. But thank you all for joining. I do have to like hop on another call, so I'll be leaving now. But is there anything else, Luke, that you want to add?